again, just welcoming you all. And I thought it makes sense to talk about two technology inflections. Thanks for setting that pace, Nirmal. And so for all the people on the call, I'm making a presumption here that you may or may not have heard about, IoT architectures or the main pillars of 5G. But my intent and promise to you in the next maybe 2 hours is to demystify three aspects, right? And that's where I thought we kind of, take this at that level. And one is the architecture aspect, which is what are the pivots, what constitutes 5G, and how is it actually linked to the next evolution for massive IoT? And we'll demystify that too. There's a reason I put that as massive IoT. This might mean different things to different people, but at all points of time, what it really envisages is that you make sure you understand what's really happening. There are so many IoT markets going around. Just quickly turn on this video. Okay, all right. Just turn on my video as well. So I wanted all of you folks to get that IoT had a lot of background in terms of almost 4.5 decades of evolution, but 5G promises to take this premise to the next level in terms of service architectures, technical architectures, radio architectures, transport architectures. So let's just demystify that. It's a simple math model: first stage, second stage, third stage, fourth stage, and the fifth stage. And so who I am, just a quick introduction. Not going to spend more time on this. What I do as part of my role in Cisco, and I've been in this company, and I sometimes jokingly say that it's one job, many careers, because Cisco gives you an opportunity to rotate yourself every 2 or 2.5 years. So I've been in various roles, but my present role is really designing and architecting for service providers, enterprises, and using programmable architectures and networks with a wrapper of AI/ML security use cases. I'm not going to read all of it, but I think the last part is what I like the most. It's really developing a solution. For example, we partnered with Google and Samsung for the world's biggest 4G networks in AT&T, Verizon, Telstra, Optus, and closest to home, I don't think I need to tell anyone what Geo is. So the entire, from the radio, right, from the access to the center, telco DC cloud, most of the architecture of Geo has been done by Cisco, obviously along with partnership with Samsung on the radio side. But so I was part of that architecture team, and that's when it struck to me that this was never designed as a 4G network, right? I'm just using Geo as an example, but when you look at the scale, it was scaled to meet super duper enterprise needs, right? So in a way, 5G drives IoT. In many ways, IoT also fuels 5G to be more strict, to be more adhering to what goes on. All right. So without much ado, that's what's going to be our landscape for today, my friends. Again, as I said, I know all of you come from rich backgrounds. Saravanan and team has given me a brief synopsis of each one of you. So I thought I'll make this relevant more from an industry perspective. And of course, we'll have a lot of Q&A, right? So as this goes forward, I encourage you to sit back, have your cup of tea, coffee, if you've not had it already in the morning, or maybe a juice, like I am, and just keep your questions parked ready. I promise you I have a counter going on here. So maybe at the end of every half an hour or so, we'll take a quick logical pause, open up for Q&A if you have any, or if there are some questions in the slides, so that will make it engaging for everyone. Okay, so that's what our landscape is. We'll look at evolution, the architectures, and most important, what is really going on. Because for the first time in the history of, I would say, telecom / mobility, or whatever you call as 3G, 4G, 5G, the programmability aspects were not ignored. By ignored, I mean systems were developed more as box, proprietary, OEM legacy approach. But now we are bringing in a lot of programmability. So I wanted to look at that aspect also. So I have introduced some terms, some industry use cases like SDN, network function virtualization, and software-defined networking. And we will just look at the premise of that, right? So a lot of industry terms may be mentioned. If some of them are not native to you, just make a note and make sure you ask questions, right? As I said, we'll have scattered Q&A breaks in between. So just quickly jumping to the meat of the session is when we say 5G pillars, right? So let's look at the evolution, what's going on. And this is how not just Cisco, but the entire industry, right? The people who write the standards, so 3GPP, 5GPP, and all the bodies around it, the standards bodies, they look at 5G this way, right? It was never about, oh, we'll design it and then somebody will use it, like a factory or maybe some telco. So for the first time, it's outward in, which means the applications are driving now for the first time mobility standards. Okay, so as I promised, right, there's going to be a lot of interactive Q&A for all of you. I'll just pause here. If you look at this date, can some of you associate what is so special about this date? I'll take a few seconds pause, let this sink in. Anything special about this date? Yeah, I know it's slightly back, slightly 13 years back, but I'll give you a clue. This was really, in a way, I know it's not so significant about the date, but I think what happened on the date was the iPhone got launched. I'm just using that as a symbol. And that heralded the application evolution, right? For the first time, people started looking at the software world, which is apps, residing on a hypervisor or OS, which is the mobile OS, influencing certain things. So whether it could be a robotic arm in a Bosch or a BMW or a Toyota or a Mahindra or a Maruti Suzuki factory, or the vision for partially or driving assisted cars. At that point of time, Tesla was in the blueprint, mind you, but Tesla was watching closely what would it take really to have a 5-stage evolution for cars. And just like we are now going for completely code to fix and click to fix kind of an approach. Also the world of UAV, and that's very interesting as well. And these are all three huge mega trends. But when I mean UAV, I mean unmanned aerial vehicles, right? Or drones as one manifestation of them. And then there is so much technological evolution for drones as well. And they themselves have now become application, right? So you could look at a drone or a robotic arm as a mini system. So CPU, IO mem, input output, a little bit cache, and now the ability to sense, right? And sense and detect. So when I mix this together, as human beings, we are given by our creators 5 senses, right? So we hear, we touch, we taste, we see, and we smell. All of that works together in a perfect fashion, right? So while you're typing, your fingers are, kind of, touching your keyboard or touching the surface. You're drinking something, you're seeing something, you're hearing something, you're smelling something at all the time. So this amazing world, I know none of the sensor fusion world is at that, but we are partially now going to a linear or a one-dimensional world of sensors, wherein a robotic arm can sense how far the chassis in the body shop has come and make a very calculated decisions. And on top of that is a world of data insights, is a world of edge compute, is a world of augmented, virtual, and hybrid reality. So I know we are talking a lot, but at the core, I believe it is going to be this huge mega trend driving force of 5G and massive IoT, which is really going to drive this safely, at least for the next 1.5 decade. Okay, so 2020 to 2032 at least, till we really start looking beyond 5G. And I honestly think we haven't even scratched the surface yet. As you all know, for people following 5G standards, India is looking at a sub 4 gigahertz, so between 3.5 to 4 gig is where we're trying, but that again is clashing with the space center frequency. So while we sort the sub 6 debate on what highways we should use, because highways are everything, the spectrum is everything, right? We have to decide that we get the sizable and the most feasible chunk for all operators. But we are also going to talk about a little bit on that, but more from a platform perspective. Okay, so we'll jump into the 5G technical pillars, but before that, as I said, let's also do our journey as outward in. So by that I mean, why 5G? right? Why? We are pretty okay with getting 25 megs. I'm sure all of you, probably some of you may have even logged in through your phones. It's a very reliable bandwidth to have WebEx audio, the unified collaboration platform we are all now seeing and watching each other. So what is the need for 5G? What is this special thing, right? So this is just a minimum technical requirements. The TR do not mandate, but there is a minimum threshold you have to achieve. So that's what I have put here. But I think the triangle, the pyramid on the right hand side, if you're looking at it, so that's what's really going to excite people, right? And I put some use cases, industry use cases, but give it a few seconds. Try to look at this, right? So if you really say enhanced mobile broadband, okay, you're really talking about capacity enhancement. So again, just if you look at your cell phones, from the traditional whatever radio antennas you had on your phone for mobile data, if you can now jump up from 25 megs of LTE 4G to almost a factor of 10 or 15 times more, so at least 250 to 350 or even 500 megs, that is what is the capacity we are talking about. Although the standards and the back-end testing, for example, the test bed which Cisco is doing with Indian Institute of Science here, so we have tested for almost a gig on the phone, right? So it's so 1.3 gigs is what we are getting, but that's obviously in the labs, and when we put it out on the cell towers, it's going to change. But at least a gig is what people say. So that's the first one, if I may say so. If you imagine the triangle as three ones, the first one is 1 gigabit of speed, or the enhanced mobile broadband. And I will leave you with that thought, my friends. If you have a potential even of half a gig, which is 500 megs, or 1 gig on your cell phone, would you not prefer to let go of your residential broadband, right, or your fiber provider? Just food for thought. Okay. The second one, and that's the bottom left, and that's the part where our architectures also meet, is massive IoT. So earlier with 4G, yes, you have the potential to link up to tens or maybe even slightly thousands of devices, okay, a half a thousands or maybe just over 1,000. With 5G and the service plane, and we'll look at the pillars driving that. And if you look closely at the icons, we're floor having maybe 500,000 parts or 1 million parts. So the second one is really 1 million or 1 billion connected things. So suddenly the scale changes from thousands to 1 billion connected things, 1 billion. The one is also hypothetical. It can even be 1 million, 1 billion. But the highway of 5G, which is the spectrum, the transport, and the core, all of them support and can scale up to 1 billion devices. So suddenly now your smart city itself is provided as a service on a 5G network, right? So I'll say this again, because this is the world of SaaS, right? Software as a service. Everything which happens in your city or your community, I prefer to use the word smart community instead of a city. Everything, the millions of citizens, so 10 lakh, 40 lakh, 4 million, 10 million citizens in a metro like Bangalore, Chennai, Mumbai, Pune, Indore, Nagpur, all of them and all their needs can be serviced. Not with one network, but I'm just saying the network or the fabric of 5G can support that. Okay, the third one, really at the bottom right of the triangle, is the most interesting one. And if I may say so by interesting, it is the most challenging one. And let's look at, why is it most challenging? So when we say URLLC, ultra reliable low latency communications, or low latency communication, LLC if you prefer. We're talking about, again, if you use a human example, we all may not realize, but our senses really operate in the millisecond speed, right? We take probably 1/4 of a second sometimes just to smell and interpret that data and say, oh, this is the smell of orange juice versus a tea coffee versus just plain sandwich. Okay, 1/4 of a second, 250 milliseconds roughly. So if you imagine that 1/4 or maybe 1/10 of a second, so 100 to 250 milliseconds, that was the latency budget of 4G. 5G promises to bring that down to tens. When I say tens, I mean 10, 20, in the worst case 40. I think 40 itself is huge. So, being technological purist guys, we have put 1 millisecond. So that is the third one. So that's a nice way to imagine the 5G pyramid. 1 gigabit, 1 billion things, 1 millisecond, three ones, right? That is the play of three ones. And why do you need three ones? So if you look at the applications near that vertex of low latency, you'll find connected cars, you'll find vehicular automation, um, self-driving, connected cars, partially connected cars, most important, even telemedicine, telesurgery, a lot of those things, they require that latency. So think about it for a certain time when you make a call, and if it's a video call, or if you're watching this WebEx video now through your cell phone, you're probably the delay budget, end to end of maybe 200 to 250 or 175 milliseconds. Now we're talking about bringing that down again by a factor of 10. So that's the place really where SDN, software defined networking, makes an impact. You cannot potentially push the physics and the electromagnetics at the radio side to achieve that latency because it has to be end to end. And then you have to displace certain network functions which were being processed there and bring them closer to the radio side. And that is what mobile edge computing is all about. And mind you, latency is not just low delay, it has the reliability aspect also to it. So which means it should be low delay and there should be less packet drops. Why? Because if Subodh is getting operated here in Bangalore or in Mumbai, and my doctor is sitting in Boston or in Chennai or in Hyderabad, then a latency of more than 100 milliseconds is actually going to send the wrong signal for actions for remote surgery. Think about two cars exchanging information. I know it sounds futuristic, but in certain parts of the world, it is being done. There are cars or vehicles talking to the infrastructure, which means talking to the traffic lights, talking to the speed breakers, talking to the roadside curbs, and talking to other vehicles of the same type and exchanging data. And that has to be at real time, so closest to the real time. So connection density, billions of things, and all those things come into play. So I'll just repeat the technical jargons used are EMBB, Enhanced Mobile Broadband, MMTC, so Massive Machine Type Communications, and URLLC, Ultra Reliable Low Latency Communications. This pretty much is what the standards body, whichever you follow for 5G, has decided. And once 3GPP decides, they do all that, the structured approach, which they've been doing for the last 4 decades. And then they give it to the connected bodies also. So the Open RAN forum follows it. The IETF, right? The people who write the data protocols for transport and core, the RFCs, they follow it as well. The optical guys follow it, and so on. Okay. And then there is connected, for example, 5G AA, right? Automobile Association, which solely looks at how 5G will drive connected cars, right? Or partially connected cars. They also follow it. All right. So let's quickly break this down, right? Just going further now, this is like a double click on why are we really talking, right? At the end of it, remember folks, till 3G, it was really just simple voice with a lot of SMSs. So basically textual characters up to say 502 bytes going, not much of a constraint for bandwidth. And then post 3.5G, which is with high speed packet networks and a little bit of 4G, mobile networks changed from really, I would say, normal networks to TCP/IP slash IP networks. And there was a lot of TCP/IP slash Ethernet coming in, but in normal networks, whichever office or college or research institute or business you run in, if you look at your Ethernet cables, right, or if you look at your LAN or even your wireless LAN networks now, the standard networking primitives is the same. There's bandwidth, there's latency, and there's reliability, right? So bandwidth, how fast, how further, how much clock speed and all that. Latency, right? Round trip time delays people are calculating. And with latency, just for voice and video, there is a difference, right? If you imagine two bogies of a train, you have to ensure that the coupling between the two trains is exactly, say, 2 meters. Okay, it cannot be less, it cannot be more. So that is like a jitter, as we call it, the delay variation in latency. So when you're sending voice or video packets, you cannot have PDV, packet delay variation, or jitter. If there's a lot of jitter, they will start making noise. So you'll start hearing something like, instead of cake, for cake of eating, you'll start hearing something like ache, bake, take, lake, rake. So it has to be very clear. And then the reliability part, okay? So there should not be any drops. Packet drops in a corporate network, packet drops at a wireless hotspot are okay, because at the application layer, beyond layer 4, so 5, 6, 7, right? Session, presentation, application, you can have retransmissions. Packet loss, when that payload is carrying medicine data, when that payload is exchanging data to a robotic arm, when that payload is pushing data to the next car, simply means very disastrous results, right? You cannot afford to. So that's why we, for the first time now, the telecom world, the IT, LAN, WAN, WLAN world, and the industrial world are coming together. That's how I would urge you to look at 5G. If you were to simplistically explain this within your research circles or your students, it's really like network of networks. It is the way now networks will evolve, whichever network you look at. So LAN, MAN, WAN, PAN, HAN, even your home area networks, right? Because everything is now converging. All right. So this is how the evolution is happening as we speak, right? More than 85% or 90%, I would say, uh, of all the telcos. When I say telco, I mean telecom companies like Geo, Vodafone Idea, or VI, or Airtel closer to home, or Telstra, Optus, right, or PLDT in Philippines, Rakuten in Japan. These are the people who are already there at 4G, and vice versa on the Western side or on the Europe side. You have O2 and obviously T-Mobile, Sprint, AT&T, Verizon. So most of these people, if you look at the top, that's a simple stack architecture of 4G, right? So you have the device, which we, just give it a flowery name like a user equipment. And then there is a way in which it connects to the RAN, right? So there is a radio unit, and there is a baseband unit, and then there is a cell site router. Okay, and this together constitutes, if you look at the RU and the baseband unit, is what we call on the cell site tower, right? Which if you look out of your window, that the tall structure, cell site tower, pretty much has this: the radio unit, the baseband unit, and a fiber connecting it to the ground, going into the cell site router. And consider 10,000 of you latching on to one cell site tower at least for 4G, and then it goes to a BBU hotel router, like an aggregation point. And so that part till the aggregation is called as a front hall, because it faces your mobile. And then there is a part beyond it, right, beyond the aggregation, and that is called as a back hall. And then at the back, obviously, I put some terms there, but for people who may not have seen the evolution, from 1999, most of the service providers switched from BGP IP network to MPLS networks, right? So multi-protocol label switching. It's a very fast way to switch and route packets on an IP world. It simply means, okay, I'm Subodh. My label is 10. What's your label, and where can you route me to? Instead of worrying about how far you are, what is your links cost, how much further can you send me? It's a simple and efficient way to route. So it's like a layer on top, right? And it works very well with BGP, which is the routing protocol of the internet. So all that thing is the core. And then that core connects you, whether you want to, browse on your mobile device, you'll go to the internet, whether you want to fetch some more data, download something, so push or pull mechanisms, then it will connect you to the CDC or just plain DC, right? And or people also call it telco DC. And that EPC, which you see, is called as an evolved packet core. It's just a fancy term. For people from the 3G world or earlier world, you might have heard about mobile packet core. So EPC is just an evolution in 4G for mobile packet core. right? Now, if you look at that 4G distributed RAN, right? So you had RANs, or the radio access network was distributed. Most of the people also kind of, had centralized their RAN. So there was a mix of centralized. I would say now 85% of all 4G networks are following the CRAN, or the centralized RAN approach. Now, what happens for the first time is just like an iPhone. I'm using again that, iPhone, or I'll just use the term smartphone. Whether it's Android, Samsung, Microsoft, or Apple, doesn't matter. Just say, let's just use the word, what smartphone did to your browsing, net banking, your gaming, anything in which you track data, is what now 5G and its architecture principles are doing for telecom mobile networks. So with 5G, the C becomes now Cloud RAN. And this is what happens, right? So you again have the same connection, but now you actually split it. You split it in software and bring that portions of the network. So this is all still the front haul part, right? From your phone to the first router, which is placed right near your cell site tower, assuming whenever we have 5G in India. So instead of enhanced node B, it's called as G node B, next generation. Or so 5G towers are also called as G node Bs. So on the G node B, the Cloud RAN approach, and with an enhanced protocol, radio protocol called as eCPRI or eCPRI. Okay, that's what really makes sure that you get the same treatment like Ethernet. So in your LAN, Ethernet had scaled from almost, I believe, 10 or 100 megabits all the way now to 400 gigabits. That's how it much has scaled. So eCPRI gives you the same deterministic approach for radio packets. So it's like radio on Ethernet. So enhanced common primary radio interface. You can look up the specs if you like. And that now splits your front haul, and it brings your data unit or your distributed unit and the control unit closer to the place. So what it means for, say, Subodh browsing on 5G. If I'm browsing a lot of, say, Global Technical Forum videos, right? Or say SDN Central, or any summits, any IEEE summits, or any research summits on YouTube. And if that content was in the data center far in the right, okay, right here. Let me see if I can annotate. Okay. All right. Yeah. Okay. So if you look at this, right? So if the content was here, if you're looking at my screen, yeah. For the first few milliseconds, the content is fetched. So it will go from all these 5 stages of router. And then just a few milliseconds later, most of this content, by virtue of software, will be cached here. Right? That is what really happens right now. Everywhere. In fact, all of your ISPs from whichever part of the world or the country you're operating, most of the ISPs use web caching, and they cache almost 80%. Right? So Reliance Jio would mirror the entire internet content closer to the data centers in New Bombay, and everything only for things like Akamai or something. If you actually do a trace route, you'll notice we always go through Akamai, which are like web caching operators, right? So it is very, very imperative that you know what you have, and then the first pages come from there, and then it's all cached. So it's all a function of, as more people start using the same site, the decision gets made in software what gets moved closer to the ground. It's one of the principles, not the core principle. It's one of the principles also for web caching. It also is the primary reason why, you know, I'm going to use this term. If you look at it, blue arrow below, E2E network slicing, end-to-end network slicing. So traditionally, imagine your home network, imagine your college campus or your business network, let's say in a building with 17 or 20 floors. You always have a segregation. These are the sales people, finance people, HR people, legal people, sales support people, IT people, security people, and their little networks get the treatment. The technical word is called as quality of service, or in mobility world, it's called as quality of experience, QoS, QoE. Network slicing really makes virtual networks and promises, whether you are a mobile device, a factory, a tablet, a connected car, you actually can demand from the network. When I say demand, I mean you can negotiate and say, I want this treatment. Hey, I'm a factory, I'm a robotic arm. I cannot afford to have latency more than 250 milliseconds, because you know what will happen? I delay my production lines. Or if you are just plain browsing packets, you can tolerate huge latency budgets. Okay, so all the decisions get made. So now the front hall is now split. So the DU and the CU itself is split. So that's why it's called as a mid hall. There is a layer in between. So front hall, mid hall, back hall. Just to make it simple, we just say X hall, right? We don't spend a lot of times just doing that. Right? Pardon me here. Okay. So just wanted you guys to get that feel that it's very imperative that when you look at mobile edge compute, this is the premise. Okay, mobile edge compute. So it brings closer to the edge, computes. So that green, blue, orange, that stack which you see is nothing but a stack of x86 servers. So open servers, very high speed servers, which can cache and virtualize routing functions, firewall functions, web content functions, caching, load balancer, you name it. And that happens by virtue of network function virtualization or other terms. But just wanted to make it clear. And that's why, while on the far right, you have, if you're looking at centralized data center or CDC, closer to the edge, you don't need to mirror all of that, but you can have multiple 500 or maybe 1,000 micro data centers. And that is a cardinal difference. So hence, it becomes split, because for the first time, you're now separating the radio part, right? So you have G node B, DU, G node B, CU, control unit, data unit, or distributed unit, right? And that's why it becomes very imperative that you get this right, that in a front hall, all that matters is how is your network going to service the clients? What do you want? Which is the data? Which is the APIs? Which is the protocols you want to service? And that's the premise. Now, terms you will hear often is called as network disaggregation or decomposition. It simply means, the nicest example I can give is, let's look at tea, right? Some people prefer to make tea with plain water, boil, add tea leaves, and then add the spices, jaggery. Some people just take maybe half a liter of milk, boil, add water, and do it. So either way, you're decomposing the tea, right? If you look at the constituents, 3 or 4 constituents, you can add them in any fashion as per your needs. And that's what we are really doing on the radio side, the transport side, which means beyond the backhaul, all the way till the core. I've just given the core as a ring, but it's really a huge national ring, right? It could be many layers, maybe 50 or hundreds of core routers, very high speed, at least I would say 40, 20 terabit per second per interface speed routers, right? So as you move from the left, you move from, 10,000s or even 1 lakh kind of devices. Then you come to the pre-ag, you're at thousands. At the core, you're at hundreds or 50s. And then the data center, you could be 10s or 20s, even 3 or 4 data centers. For example, Geo could have one data center in New Bombay, obviously, one backup there itself, and then one primary or disaster recovery site somewhere, maybe in Bangalore or Hyderabad. So that's how it goes. Okay, let me take a quick pause here because I think we're pretty deep and it's almost been half an hour. If Hey Naresh, if you're around, if there's any questions anyone has, I can just take a quick pause and answer them.
There are no questions, so we can continue.
Okay, okay. Just a quick check since I got you. Is the video okay? Is the audio okay? Are you hearing any choppy noises?
No, everything is coming out perfectly fine.
Okay, okay, wonderful. All right. So then let's, with that segue of the LTE to 5G. And by the way, LTE is just a long-term evolution, as they call it. So that was supposed to be how the system, right, of mobile networks will evolve. So in that, the 4th generation was the first time TCP/IP data, and even, if I may use the word, the next evolution of internet, which is called as IP version 6, right, which can cater to almost billions and billions of IP addresses. that came in. 5G now takes that promise further. Okay, so even the version of internet, which was IP version 4, is no longer relevant. For those of you who are interested, even if you look at your mobile phone when you're browsing, if you really look, you'll actually find an IP address which is all hexadecimal, right? So instead of 32 bits, like, instead of 10.10.1.2, which is a dotted decimal IP version 4 address, you'll find something like 4CEF, right? So from 32 bits, we are scaling to 128 bits. So 2 to the power of 128 is the number of possibilities you get with IP version 6 or IP next generation. And that is completely sufficient, and much more room is left even for space communications, okay, which is pretty good. So now just touching the first pillar again, and I know this will get slightly intense again, but we'll now slightly, just make sure everyone is on the same page. So now we're just talking on the radio side. So for all of you folks, I'm just, if you imagine the 7-layer stack, physical, data, network, transport, session, presentation, application. Similarly, on the radio stack, right, you have this stack. So radio resource control, packet data convergence protocol, and then there is a high and a low stack for RLC, radio logical controller. Then there is a high and low MAC. So physical, MAC, RLC, PDCP, RRC. Even at the radio level, if you imagine a 5 or 6 level stack, you can now decide how you want it. So you can have a, as they say, split. I'll split my stack. I'll put certain functions here and certain functions here. And that is why it's called as a control user plane split. Control, more like signaling. Hello, why, please do, give me this response. User plane, actually carrying the data, right? So control plane, data plane, user or data plane. So even the RAN protocol is now split. And based on this, if you look closely, I've written it in small, so pardon for that, but there are 8 possible options in which you can split. Okay, so that's why in 5G architectures, the moment you say, I'm designing a 5G, if you go to a Rakuten or Geo platforms, they'll always say, are you using option 2 or option 7 or option 5, whichever. And if you look at it, so option 1 all the way to option 7 or 8. So those are the ones which are given there. You can even look at high-level split between the data and the control unit, right? That's completely flexible. Or you can have a low-level split between the radio and the centralized LAN. So all of the options are coming here. And the way I would read this is, it's more about tweaking and controlling. If you start doing strict options or slicing more, you get the bandwidth gains, but you might lose out on the cost and the complexity, right? So that's why the 2 triangles which you see here, edge proximity cost and the centralized gains and the latency bandwidth requirements. Okay, so this is how it looks at in real life, right? This is when you go to a 5G tower and open your eyes and look what's inside. So that's the dual split. So you can have a centralized RAN right now. I hope the color coding is clear. I can, let me see if I can annotate this part. Okay, so this is the architecture right now, which is there on almost most of the 4G guys. This is how it looks right now. And okay, this also would be a popular one. Okay, now we can do a split, high-level split, or a high-level, low-level split. So the middle 3 are options when 5G will change, how it looks like. Okay, just quickly going ahead. Let me know if this. So this now, people are now talking about small cells. By small cells, I mean, think about an IPL stadium, right? Because cricket is the flavor of the month. Think about a small apartment building, 5 or 6 floors. Can I have a small cell just for them? Can I have a small cell just for a group of offices in, say, Electronic City or any software zone? And a lot of things can come up, a lot of possibilities can come up. So there is this hierarchical stack, and there is this, as we say, tier 1, tier 2, where you can absolutely dictate what is my transport latency and make sure the network services that. I've given some indicators, but you can make out, if you remember the terms, EMBB demands, say, 10 milliseconds, right? Whereas URLC is going to be very harsh. You cannot really go beyond 10 to 15 milliseconds, right? For URLC kind of applications. And then, so the simple logic is, what is the application demanding? Map it to, say, slice type URLLC. That slice type will tell totally to the network. I cannot have a latency more than 15 milliseconds. I cannot have a transport latency more than, say, 2 milliseconds. And the number of sites I can cross is this much. So that is what keeps on happening. This is just the same previous slide mapped to the three options. I'll quickly go ahead. Because this is the part where I think all of you will be keen. As I said, right? So common public radio interface, CPRI, earlier till 4G was the standard, but then CPRI was like this. We are all in a room. When I'm speaking, no one speaks, right? So typically like a time slot. But because I'm not speaking for 10 seconds, those 10 seconds are wasted. eCPRI is the next evolution, right? So enhanced common public radio interface will make sure if I'm not speaking, someone else in the room can done. So Naresh can quickly use that 10 seconds and push packets on the wire. And that's why it's called as, from simple time slot, it is statistical time slot or time division multiplexing, pretty much what Ethernet does, right? Hey, who's the station on the wire? Who wants to speak? And for people following IEEE standards, so radio on Ethernet 19.1, so 1914.1, but then next generation frame interleave, right? So 1914.3. So you can actually, by interleave, I mean, oh, this is a data packet, this is a voice packet, and you can actually interleave them and do all kinds of specifications. So for anyone following this, so IEEE standard 1914.1, that is the eCPRI basic standard, radio over Ethernet. 1914.3 makes sure that voice and video gets precedence. And then 802.1 CM, you might have noticed the similarity between your, so that typically is like your Ethernet, it spawns from the Ethernet standard 802.11 or wireless LAN. So you can have TSN profiles. So by TSN, I mean time sensitive networking. Everything is a function of time. Right? All the million packets flowing across have to be in sync. They all have to make sure they're aligned for time, phase, and frequency. These are the three things. In 4G, phase was not so important. Fortunately or unfortunately, in 5G, phase is equally important. So you have to really design and architecture networks that way. The third standard body is really RAN. So very glad to say most of the Huawei's, Ericsson, Nokia, Cisco, most of these vendors, right, who had proprietary interfaces, Siemens and all those, we have now embraced Open RAN Alliance, right? So bring a server, roll out the software functions, and enjoy the benefits, right? That's how it really translates to. Okay. And that's what we mean by deterministic. When I say deterministic Ethernet, it's like oil and water, right? Ethernet was always supposed to be best of all. It was like IP, Internet Protocol, right? Throw the packet, hopefully it goes. If it doesn't go, well, the upper layers will ask for a retransmission. So that was really, but now for the last 8 odd years, Ethernet in Metro Ethernet, WANs, has now really changed to deterministic Ethernet. So everything is acknowledged, it's well timed, and there's so much connection, link layer management functions. So 802.1 CM connection management takes time sensitive networking and applies it to CPRI over packet, right? Front haul. So now you can have separate flows by priority, by VLAN ID. So each VLAN, remember, maps to what network or function type you want. I've just given the Metro Ethernet function uni, but don't worry too much about it. For people interested, just Google for Metro Ethernet forum. You'll get the standards. The important takeaway from the slide is frame preemption. Okay, so 802.1 CM basically puts two highways. One is a normal highway. Let's say the radio is transmitting packets, which is radio B, and you can even have a strict highway. So the moment I notice there is a connected car packet, I can actually preempt the frame, So there is frame preemption and interspersing express traffic. So when in absence of extremely critical voice video, just transmit data at the committed speeds. The moment that streaming video packet comes in, don't pause it, don't pause data, but create room for that video traffic, because that is very sensitive for delays and reliability. All right. This is pretty much multi-access edge compute, as we call it, the basic premise. Again, I'll give an example. When you're churning and processing and storing and routing and doing analytics all at one central place, it's great, but it has certain disadvantages. You are limited by that. There's a single point of failure. Most important, as network gets layered, you have to traverse all the way. So multi-access, or it was earlier called as mobile edge compute. I prefer the term multi-access edge compute, MEC, as it's known as. It's basically about pushing the devices closer. So who's generating the data? In a city, in a smart city or a smart community, millions of citizens roaming around on bus stops are generating data closer to the ground. So if there is a LoRa network, or if there is a narrowband IoT network, that should be closer to the ground, not being processed on some data center server at the end of the city. So that's why you have all this edge offload, latency reduction, data reduction, and then you do compute, storage, routing, and analytics closer to the ground. So, what is the immediate benefit? How does this translate? Think about a smart city deployment, let's say in New Bombay or Bangalore. I know Hyderabad in Telangana has it. I know Raipur has it. I know there are some places in Belgavi and Hubli where we have done this. Bombay, I think more than 4,000 traffic signals, and all the 12 national expressways, right? So Mumbai, Pune, or Pune, Bangalore, all the national highways now at certain points have IPTV cameras, CCTV cameras, right? So this is how it works. So if you're driving, say, above 90, which is the prescribed speed limit, up to 5 or 10% is allowed. So if you're above 100, and then the CCTV camera traps your image in which whoever was in the car, it's your driver, you, or your family driving it, and the license plate number. So there is two-factor authentication. And the moment you pass that area with that high speed, it just clicks and captures. Now, there is no point to do that analysis, map your license number, go on the M Parivahan server, or go to the Aadhaar server, link it to your Aadhaar, and do all that. So within, say, 10 milliseconds, a challan is pushed to your phone. So all that data consolidation is a finest example of edge compute. Within 10 to 12 seconds, the camera, when it takes a picture, gets your license plate number. So let's just say maybe, MH011234. That vehicle belongs to, say, Subodh Gazre. And okay, he's residing here. His Aadhaar ID, his license number, say, whatever, MH5678. And then the challan is pushed out. All this decision happens because of edge compute. If all this decision was being done high up in the cloud, it would take more than 2 or 3 minutes, right? And then you're just losing out on that. So that's what the mobile, or the multi-access edge compute premise is all about. And network slicing actually comes very close up. So I'm not going to read out all of this, but again, the typical 5 stages I've just given. So the user equipment, cell-side access, hub aggregation, central office, or the mobile service operator, and the data center. Okay. If you look at the number of things, as I told you, right, from the leftmost to the rightmost, the number of devices keep on reducing, but the constraints also keep on increasing or decreasing. And that's why you have to make sure the edge compute means you're moving closer to the left-hand side here of this table or the service plane. And then you make sure you give centric, right, device centric. If you are, for example, around in a mall, and if you get an income tax notification, it doesn't mean anything. If you're in a mall and you get e-coupon or a voucher, it means something, right? It's a context sensitive thing. So similar thing, right? So, and then within the constraints of space, power, environment, you can do all of these requirements. Finally, 5G is really going to be about placing all of these entities and making sure you extract with software-defined networking. And there is something beyond the cell-site router, and it's called as segment routing. So SR, that is a protocol, which is going to be, I would say, the next evolution of MPLS, IP MPLS. And that also makes sure. So it's pretty much about, you have to make sure the transport and the core is completely aligned. So segment routing is, before even you start talking, are you sure you have the bandwidth to talk on this channel, right? So segment routing is pretty much that. It's like source-based routing in a way, but modified. with precise deterministic control data plane. And then you have network function virtualization, and then everything has to be orchestrated in software. So think from a Bharti Airtel or a Reliance Jio's perspective, they would not buy any 5G network, or they would not even roll out any 5G solution if the time it takes to onboard. For example, you go to say Jio.com, you say, I'm an existing Jio user, I want a 5G SIM. They give you a eSIM, and within 12 seconds, you suddenly are online, onboarded, as they call it, right? So Jio disrupted the market. They did onboarding of subscribers with eKYC for the first time in the history of Indian telecom, right? So the traditional model earlier, before I think to 2016, was okay, submit say 5 or 6 user ID proofs, address proof, and whatnot, statements and everything. Take 3 days for SIM activation, and the fourth day, then you start getting calls, or maybe 24 hours. Here, they just ask for your 12-digit Aadhaar number, which is mapped to everything. And even by the time you submit your Aadhaar number, within 2.5 to 3 hours, they onboarded users, and now they're doing it in less than probably 1 hour. So I think with 5G, it will even come down. So that onboarding time is everything, right? Because the user has displayed interest. You've either gone to a portal, walked to a store, Vodafone, Airtel, or a Geo store. You've displayed interest. You cannot wait for 2 or 3 days to have service because, as you all know, next to food, clothing, and shelter, we all like to be connected for whatever reasons. We want it, although we may not do anything in that next 2 hours, but we want to be connected. I'm not saying from a gadget perspective, from a service perspective. Right. So let's quickly look at slicing concepts, right? Again, as I told you, three main service families, right? So MIoT, massive IoT, EMBB, and URLC services. So think of them as 1, 2, 3 slice. So within software, there will be a network slice instance, which will aggregate all of this network slice subnet instance. Okay, so every packet pretty much goes from the RAN side. Okay, my NSSC or NC is this. If you look at the little diagram, so MMTC packet 1, slice number or slice ID as they call it, EMBB say 2, and if you look at URLC, look at the latency as compared to the other two ones. So high density, supporting what, supportability, reliability, bandwidth, latency, maximum transmission unit or MTU as we call it. So different things happen. This is how we envision. These are all software flows. There are certain 5G constructs I've put here. So imagine a car versus a mobile versus a mobile on a video call. So the car, okay, all of them will go through the cell site tower, which is the 5G tower or the 4G enhanced tower, but they will demand different things from the network. A Mercedes IoT connected car versus, say, a Delphi onboard car unit versus plain internet browsing versus, say, internet browsing with video streaming. They all will demand different things from the network. So the top three blocks which you see in Indigo, so user or user defined or device management, right? Or network slice function, right? Or network reliability function, network resource function. How are you going to service the networks? So these are the new. So in 4G, all the network interfaces had S services. In 5G, we have really taken that S to the next level, and that's why we have all N. So N1, N2, right, on the access side, all the way till N15, I believe. And you can look up all of this in the architecture specs. Okay, so a simple thing is VPN, right? Virtual private network. So L2, L3 VPNs, they are mapped to the slice plane. If the slice plane is yellow, low latency, that's the treatment we'll get end to end, from the radio to the access, to the transport, to the core, through the data center. And so the green and the yellow part is at the API level, but the gray part is what actually happens, the physical level, right? So there's logical and there's physical. This is how the string of routers is just a suggested design. Sometimes you'll have 5,000 of these routers connected, but they will all steer. They will all steer based on your slice number, slice type, slice attributes. So connection density, reliability, latency, delay, MTU, all these things will be defined in the slice type, which means traffic is classified and controlled at the ingress itself. So you classify, okay, all people. So for example, all people entering this room, okay, and then you say all people wearing blue shirts enter and go and sit on this side. All people wearing blue shirts with collar. So you classify, mark, police, shape, schedule, and then put packets. And all of this we're talking about in nanoseconds, not even milliseconds, right? Because you cannot afford to do all this transactions and then introduce delay just for doing them. And hence the need for a converged 5G automation solution. So I'll say this again, when I say converged, I mean, are you fully aware what goes on in convergence, right? So at a large, the blue layer is what we started with. Segment routing or path computation element is the service orchestration. So that's how people will troubleshoot networks, will design networks. It's just like phone banking, right? You used to call bank, IVR, press 2, press 5, press 7. From IVR, we went to net banking. So type hdfc.com, ICICI Bank, SBI.com. Look at app banking. You're not typing anything. You have an app. The app provides the artifacts and eliminates phone banking, net banking. So you log in through an app. Your top 20 things which you do with the bank are all just click, 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 click. If something times out doesn't go, you just come back and do it again, right? So that green layer is pretty much like that appification layer for networks. And the blue and the orange layer are the traditional legacy, I may say. So they will always be there. So segment routing, right? As we told about segment routing with MPLS, segment routing for IP version 6, for path management. And then IEEE 1588 is a timing protocol. It's also called as PTP, right? So it's like a timing protocol, and it will take care of your phase, frequency, and time. So if you imagine your sinusoidal waves, are you in phase? Are you in sync? And are you timed perfectly? So that takes care of it on the transport side. So this is just a visual representation really at the if I may say, so the control plane of routing, right, which is segment routing, which is service aware traffic steering. So as I said, right, you can steer traffic as per the policy. So let's look at, say, traffic wants to go from node 1 to node 7. So 1, green, 7, right? So that's what you're putting. So let's say traffic which is destined for 10.10.10.1. Okay, so it goes from 1, node number 1 or router 1, 2, 4, 6, 7. At the same time, while it is doing that, it builds a backup route. And that backup route is called as mutually exclusive route, which means if you notice 1, 3, 5, and 7 is also built in software. The moment anything happens to green, it can just switch over. Just like fiber, if you notice, the reason fiber rings, right? They just switch less than 50 milliseconds. If Mumbai-Delhi fiber gets cut, there's always a backup ring. And it switches. It detects within 10 and switches within 40. So 10 plus 40. Within 50 milliseconds, all the traffic is routed. None of the applications notice even a glitch. At the maximum, if you're talking, you'll just notice a dead air or a click sound, and suddenly the call will resume. You won't even probably notice on normal data transmission. Only video or voice may get impacted. So this is completely flow and destination based. And for real-time delay services, you can have path monitoring for MPLS. You can do so many things. You can simplify, monitor, troubleshoot. And I've given examples, right? So tactile internet is very futuristic, I know, but people are talking about certain special surfaces, especially military, high-end research, space research. So using your table itself, like a Zoom thing, if you noticed some for example, Marvel movies, right? You've seen Tony Stark using that simulation on a glass. So any tactile, you just press, and that just obviates, and then you do 3D modeling in there. Or for example, do the design and then just push it with your hands with augmented reality to a 3D printer. So people are talking about all of those, and that will require at least more than 250 megabits of bandwidth really per click. So a lot of those things can be optimized, right? So find the best. You can decide, find the purple route, which is delay optimized, find which has less delay, which has less loss. And at all points of time, you're probing the network, probing the network, probing the network, right? Every 3 seconds. If there's any update, change all the software routes. So SRPC, path computation element, it's an extension, and there is a TopoDB or a topology database which is built on every router. So every router maintains this, and every 3 seconds, everyone is talking to each other, saying, am I insane? Do we all know what's going to come? And this TED database or topology database will make sure using BGP, which is Border Gateway Protocol, for control and data exchanging, and then PCAP, Path Computation Element, will make sure segment routing is manifested. Okay? And your interior gateway protocols can be anything. It could be BGP, OSPF, ISIS, which routing protocols you choose. Not a problem. All right. So just quickly summarize, right? So you have slicing. The next generation of radio for 5G is rightly called as 5G NR, also called as next generation radio. And that will drive huge number of devices, intensity of speeds, and most important, that RAN having the edge compute or the mobile edge compute becomes very important. I think it's a good time to just take a quick pause and just check for any questions or comments from any of you. Very happy to receive them. Naresh, can you help me with that? I mean, feel free. You can type in your questions, and because Naresh has a view of your questions, and he can repeat the question to me, and we can answer any questions.
Uh, Most of them have just said the presentation is nice, but there are no questions except one. They've asked, can the 4G devices, be usable with the 5G technology that's going to come up? That's the only question that's there in the chat.
Mm-hmm. No, it's a good one. It's a good one, and thank you for that appreciation, all of you. I think from a device perspective, by now, remember the word we used was highways. So just like to enter a highway, you need a fast tag on your car now, right? So imagine your radio needs to be calibrated with a fast tag of 5G. So if you buy a phone which was just launched last week, obviously I'm talking about the OnePlus and the iPhone 5G or whatever you call it. So unless the phone says it is compatible or 5G compatible, um, you will have to buy a new phone. So your existing phones, if they're not, because they need to talk on those frequencies, just to differentiate, you have a fast tag now which operates below 2 gigahertz. 5G will necessarily be above between 2 and 6 gigahertz, at least for India and most of the operators. And there is a chance we might reuse some of the bandwidth. So sub gigahertz will be reused, but they will always look at dual band, right? So, and that is the way all OEM, right? At least device makers wants to make money. So I'm sure you'll get attractive buyback plans, at least for devices. But from a home router perspective, or a campus router or your office router, it doesn't matter, right? They anyway do not talk directly to cell site towers. But your devices, which means your phones or your tablets, which basically the SIM communication, can be done. There is a middle ground. A lot of operators are looking at eSIM. So eSIM is basically software SIM, and they can actually program your existing SIM for 5G. And then if your handset supports those frequencies, because a lot of intermediate smartphones support a lot of frequencies. So if your handset is of that type, with the eSIM upgrade, you don't even need to change your handset. You should be good, right? So it all depends. Type A, totally incompatible. Type B, hybrid. Or type C, you already have a new 5G compatible phone. Then you need nothing. You just need to, when Geo goes live on 5G, just say, I want 5G. Chances are you may not even have to replace the SIM. I don't know. It's very likely. They might just program your SIM OTA on the air, and that's it. Your number is the same. The SIM gets programmed in probably 2 hours, and you're on 5G. Great question, though. If there are no more questions, Naresh, can I go ahead?
There's one more question. How the data redundancy in IoT devices will be controlled?
Okay. Great question, right? Again, a great question. So when you, if I look at this question, and if you permit me to treat it in two levels, one is from the endpoint, right? When I say IoT device, imagine your watch or even your phone itself. That's an IoT device. So there's data redundancy at the endpoint level, and there is a data redundancy at the cloud level, place where data is stored or aggregated. So right now, obviously at the endpoint level, nobody's thinking about it unless you obviously have a laptop or a phone where the signals can be duplicated. But everybody's looking at, you are generating data, you're sending data every day, or if you're just let's say electricity or a gas meter, you're sending data once every hour. Doesn't matter. All the data is stored in the cloud. In the cloud, remember, we used a term called DC, telco DC or micro DC, data center. So it has the ability to say data generated by, let's say, Naresh's smartwatch at time T1, also duplicated in the backup recovery center, say in Hyderabad. So at all points of time, as per the data privacy and the purging laws, your data is always backed up. In fact, it's backed up, I would say, at least a few more levels than just 1+1. And that's why it becomes very seamless. And you might wonder, and you might start thinking, oh my God, say 800 million people in India itself, 800 smartphones, so much data. But please look at the cloud. The cloud is really at a stage where I call it as it has crossed the exabytes, so terabytes, petabytes, exabyte, right? So we are looking at 10 to the power of 18 kind of a thing. And I think beyond exabyte, now we're looking at zettabytes already, right? So 21, 10 to the power of 21. So infinite storage really, and the cost of storing, for example, maybe before Geo was launched, the cost of storing 1 gigabyte of data, if it was 100 rupees, it's now 1 rupee on the cloud. Within 4 years, it's down to 100. I don't know where it will go next, right? But the cost of storing now itself, so people are not even talking about 1 gigabyte. People are now saying, no, no, don't store 1 gigabyte, just take storage for 100 gigabyte, right? We all know ourselves what has happened in our homes. So, two things have happened. Murphy's Law has obviously helped for compute, and IoT devices themselves have gone smarter. So earlier, if they used to have only 2 or 3 sensors, I guarantee you, if you buy a new generation phone from Samsung or OnePlus or Apple or Microsoft or Google, you could have at least less than 15, 20 sensors, right? So they're themselves storing the data. So think of each sensor having like a stack, and it stores. And even you may not even know, every time you use Wi-Fi or mobile data, it is pushing data to Android. For example, all your pictures on any Android phone are always backed up. There is nothing you can do about it. That's what happens when you say, I agree to the terms and conditions. So kind of a long answer, but yes. So operator clouds, telco DC clouds, and even devices themselves are getting smarter now. So that's the 3 level of backups I can look at. Hope that answers. Excellent questions. I like this engagement. I really love the way questions are coming. It gives me a sense of comfort and assurance. You folks are loving it. So can we? Yeah, I can wait for one more, or we can go ahead. We
We
got
can
time.
go ahead. There are no more questions, sir.
Okay. Thank you, Naresh. All right. So let's look at now. The evolution. The second part of this talk, really about digitization with IoT and all this programmability layer, right? Again, just keeping it simple, look at even mobility, the traditional world of mobility, right? Not mobile phones, but we had rickshaw pullers, we had uh, gasoline or diesel or petrol cars, then we had partially hybrid or electric cars, and then we had autonomous cars. Uh, Now, what has happened to network slash mobile network slash software world? Even the software world has gone through a similar stage. We had software which was CLI based, and then it was monitored through SNMP, Armon, and then we went to a DevOps or a click to fix or a code to fix approach. And then it's now, if you look at the final one, which is the future of autonomous cars like a Tesla, we even have a self fix model. So I don't know, not many of you may realize, but many times in SBI, especially I've noticed this, the SBI app, if you want a home loan, there is a thing called as YONO, right, on SBI. And they were the first ones actually, in India at least, to do virtual reality slash AI frameworks for home loans and consumer loans. Whatever you input constitutes your next questions, right? So the app, if you say one A plus B plus C plus D plus E, inputs are given by you, it constitutes a perfect response. Now I know you'll not buy a proposal just by talking to an AI chatbot, but anything which goes wrong in an app, it is automatically fixed in the background. In fact, for Amazon site, every Friday, if you imagine Amazon's data center, and they are our biggest customers, biggest data center, virtualized, OpenStack, and all that. Every Friday, they change their main code base. So try to imagine your phone getting a release every new Friday, and it's perfectly optimized for that. They know. So even right now, today, if they're starting a huge sale, say for the next 1 month, there is no way they can know if 10,000 people will log in every minute, and there will be 50,000 orders every hour, and 1 lakh people using the site every hour, right? They have no way to know that. All they can do is keep a tensile or a very agile network, which will self-fix. So if some people in, let's say, Mumbai or Pune experience slowness of site, automatically resources are diverted there on demand, right? That's how the networks are going, and that is the principle of digitization. That's why I use this framework. So what it really means in technical concept is all the 5G and IoT networks are going through this. It's a nice way to describe this, right? So no longer is the intelligence of routing or switching kept in a certain place, right? So which means now it's the era of SDN. So there is a software defined controller which defines the policy type, classification, marking. We saw it does the automation, it does analytics, okay, from the phone, packets from a phone using this app, browse for this much loan of this type of this tenure. So all that analytics is done. So application flows, and it's continuously learning by context, and it is driven by intent. By intent, I mean what are the users doing? So for Amazon's portal, what are the users doing? If they're always going on gadgets, electronic gadgets, because it's a Prime Day sale, accordingly, the network starts pushing and indicating the warehouses. Okay, more orders coming in, more orders coming in, right? So that's why we call it like an intuitive network. In English, intuitive means imagine all of your days when you get up in the morning, right? Since the time, if I may ask you to visualize while you're brushing your teeth, right, or while you're having a glass of milk, your brain is a super intuitive organism, and you already are planning. Okay, I have a meeting at 8:30, and then I can do a 45-minute call with my research mentors or with my team, do my second breakfast maybe between 10:30 and 11. So you're already lining it up, right? You're constantly learning, adapting, and even protecting. I'm anticipating maybe my gas delivery person or my courier wala, so I need to mute my phone, or sorry, mute my doorbell and all that, right? So you're, I'm just calling them as, security or noise threats, and you need a network which is constantly innovating, and that's why the architecture principles. I'll just let it scroll, but this is what it is, right? I'm sure all of you are doing your research. All of you talk to your research mentees and students, but this is the world now. So traditional IP address, access list based networking has now changed, and we now have a world of DevOps, right? So development, operations, it's like an infinite loop. Okay, so if you look at it, it's like the figure eight. They're constantly feeding each other. There is constant implementation. There is constant delivery. And the world of open source, containers. So imagine containers like a virtual machine with its own operating memory space. I've just mentioned scripting, Python, but don't think Python is the only one. There's so many other ways, but obviously JSON, Python, full stack, right? So Mean, Mongo, Ansible. These are some of the places, or JSON, that's where the object notification comes in. Uh, some of the ways in which IoT and 5G networks are going to be programmed. So it's declarative. By declarative, I mean I'm a human being. I need my breakfast. In my breakfast, I need, say, masala dosa. I need juice. I need tea or coffee at this temperature. And then somebody models this tea, coffee, right? So the network is now modeled using modeling languages. So for people interested, you can look at RFC 7750. There is a YAML, YAML, yet another modeling language. So irrespective of the router, doesn't matter what it is. It's as simple as when you buy a home connection, do you even bother if the provider gives you a Airtel router, a Netgear router, or a Linksys router, or a TP-Link router, or whatever you may think of. That router for you, all it matters is that black dipoles, right? It has a wireless interface. It will plug in an Ethernet, or if you're taking a fiber to home, it will plug in a yellow or orange fiber. The orange or yellow fiber of wireline is changed from one medium to a wireless medium on 2.4 or 5 gigahertz. Why? Because you want mobility. You want the ability to connect multiple devices. So at least say 6 phones, 6 tablets, 6 computers, maximum maybe 18 to 20 devices at the most, or 2 TVs maybe. And you want to move anywhere. And that's why dual band routers are now coming in, because the traditional 802.11 up to N, right, was single band 2.4. But the moment you get a cordless call on your audio phone or your microwave or your other devices like a TV talking to your media server, they also use 2.4 gigs, your Bluetooth. So there's interference. So 5G, there's a 5G or a 5 gigahertz band now, not to be confused with 5G as mobility, but there is a 5 gigahertz band now on your wireless devices. So that is modeled. The moment you turn on the router, it is modeled, it is coded. And that's the machine learning part. You may not realize, but that's what happens now. And there is now high resolution data. And by that, I mean the compute part. Someone asked me about IoT devices, right, in the break now. How can I back up? So high resolution data means, okay, data for a person riding a bike, breaking a traffic light signal at the junction of, say, Bangalore or Hyderabad, um, and his license plate being captured, right? So that APDR, automobile data, all that thing is done at real time. So license plate, registration, all that thing, you classify the data. I've just given one example, but it could be a factory, robotic arm, smart city. In a college, it could be admissions, it could be transcripts, it could be attendance. Just define the data. Okay? So declarative versus imperative, that is the way now this world of 5G will go. Okay, programmable constructs, declare what you want, the application will declare. The imperative part is the procedural part, how you code it. This is how it looks really. This is how networks are coded, by the way. Yeah, this looks, for people who are not aware, this is pretty much what a C++ in a Java object notification looks like. On the right hand side is how the main SDN server with the controller talks to the millions and millions of routers. This is typically how a Geo or a Rakuten network would look like. So YANG, right, is the way it is modeled. YANG simply means I don't care what is your label. What is the speed you're transmitting? Okay, you're a 1 gigabit interface. You have this IP address. You have this backup address. You want to transmit this much. Your reliability is this much. So YANG, YAML, if you want, these are really RESTful APIs. So REST config, RESTCONF. I think I'll go to the next slide a little better. Oh, it's not here. Okay, I'll go back here. So REST config and net config, how you program the controllers, how you program the devices, whatever may be the devices. That will tell you how it is to be. Okay, that's the modeling part. So if you now collapse all of this, right, the automation, the SDN, the IoT, the 5G part, again come back to our 3 pillars: EMBB, URLLC, MMTC. Three basic service types of 5G. We are talking about thousands and thousands of bandwidth and all that. The main application layer on top of that, I think these are the 4 areas, 4 drivers, if I may say so. Now you might think and say, oh, wait a minute, how come education institutes are not there? If you ask me, they're everywhere here, right? It could be anywhere. You have probably 1,000 to 25,000 students in your campus. We have campuses that huge. You suddenly are like a mini service provider with the cloud of your campus now to all the students. The network needs to be sliced for student activities, delivery sessions. And if you imagine, it was never so critical to have that treatment as in the last 7 months since we went from offline to the online mode of education. So if we, I'm just projecting my thoughts here, and some of you may agree or even debate with me on this. But if we had 5G now, if the whole COVID pandemic was in 2023, maybe our virtual learning experiences would have been a slightly more easier, richer, and predictable. I'm hoping, right? And this is riding on a big if that all the providers deliver that bandwidth. Okay. So that's what the evolution is. So to summarize again, these are the 5 blocks. Okay. I'll let each one build radio, open radio. So 5G, next generation radio. The first question asked today, will it be compatible with the old 4G radios? Yes, yes, yes. That's why eNode B is 4G plus 5G NR or simple 5G. 5G can scale from any G to any IP. Okay. The last bullet there is actually unlicensed radio. Um, just to differentiate, your phone is a licensed radio device. Your Wi-Fi router is an unlicensed radio device. You do not pay for using that radio frequency, right? For your wireless router or for your microwave. It is free. Everywhere in the world, everybody knows wireless LAN will use 2.4 gigs or 5 gigs. Nobody can transmit a cell phone call on that. Okay, so those are reserved. 5G even bridges this world. So Wi-Fi is now in the 6th generation. So it's called as Wi-Fi 6 802.11, A for Apple, X for xylophone, AX. That is the standard, which makes Wi-Fi behave like 4G and 5G. So that is now the convergence. So it simply means if you're home and you are on an internet call, and now you step out of your home, go beyond the range of your router, you will still be covered by a Geo or a Vodafone with 5G Wi-Fi convergence. Now, that is why it means unlicensed radio integration at the edge. That's a big promise. It's a big technical puzzle to solve for all of us architects. And we've successfully trialed it in Rakuten, which is the world's first 5G network. AT&T Verizon have gone. China Unicorn has gone. In Philippines, we have PLDT. And in India, we are running trials for 2 trials, for obviously one for Geo platforms and the second for Bharti. The second is IP transport. And this, I think we have spoken enough. So remember, front hall facing the cell site tower, mid hall, back hall, and all the transport aware solutions. Edge compute, the orange pillar, that which really brings the software the closer to home. Who's generating the data? Can I do all the compute, edge analytics, intelligence, closer, and a balance? Okay. Then there is an SDN fabric or the evolved packet core, which will have all this virtualization and all the programmable infrastructure. And last, the green pillar is orchestration. So this are the 5 pivots of 5G. Any network, right? Any vendor, any standard will have typically build a 5G network this way. And at the bottom is supposed to be end-to-end assurance and security. So it means the moment the packets start from this side, from left to right or right to left, you have to make sure you guarantee them and they're secure. It's a big thing. Nobody's talking about this, but I'm sure a lot of you already have this question in your mind that with all these millions and billions of things, will it be secure? Will it not be secure? Okay. And I've just put those words, disaggregation and automation. Let me quickly jump to the IoT part because I think we're slightly behind by 5 to 10 minutes, but I don't want to make sure that it is covered. Okay, yeah. So this is the layer, right? The API-driven layered software architecture. This is how it will happen. So whether you imagine your phone or a router now, you have your hardware chipset. The chip, for example, if you have an Apple phone, you have a A10 or a A12 ARM chipset. The Samsung also has an ARM chipset. In fact, every phone has an ARM chipset, right? What Samsung and Apple do is they have brought the architectural license from ARM, which is like Intel for mobiles, and the spin, which by spin I mean they modify the code to make it seem like Oxygen OS or iOS or Android OS, right? And then the chip SDK provides all the functions. So SAL, service abstraction layer, or adaptation layer, or the APL, and then all those things happen. Now, it's very imperative that we understand that all of this is meaningless if you don't have model-driven telemetry. Okay. So by this, I mean, this is the evolution wherein you don't have to wait. For example, let's say I'm an NMS server, all of your routers sending data to me 10, 20 seconds. Right? So I'm waiting, okay, time T0, I got 1 million packets. After 50 seconds, I get the next million packets. Now it's the reverse way. It's push-pull mechanism, much like the apps, right? Whenever you want to bank, you bank. You don't wait for the bank to update. Whenever you want to go and check your passbook, whenever you want to go and do a fund transfer, you don't. You don't wait for the bank to tell you. So it's all the push-pull mechanism. So this is another new concept, model-driven telemetry, which is a big one. Okay, and I'm going to talk about means. Sorry, it means. Okay, sorry about that. It means different things to different people. The simplest way is going back to our laptop or LAN days. You have to trust right from the hardware. The chip, is it booting from the same place? It is verifying the network OS. Is it maintaining the runtime iOS image? And that's how trust begins. If you're not trusting, and in fact, the word security is now largely talked about by trust. And the mechanism, I'm sure you have heard about, some of you have heard about blockchain, that is distributed, ledger technology. So blockchain's premises trust no one, explicit trust. Right now, the internet is implicit trust. Okay, you connect. There's a Wi-Fi protocol. You are standing in a hotel lobby, airport. You go to Hyderabad, Mumbai, Bangalore, Delhi airport. Right? Your device. You may not even bother, but you already put truckloads of data which can be compromised. That's an implicit trust you have just because you're getting free Wi-Fi. I'm not saying all of us do. Some of us still prefer our mobile data, but the temptation is there, right? With blockchain now, when really blockchain networks start coming in, it will be explicit trust. So it is something similar to if there's a courier person who comes to your home. Let's say his name is Ram or Sham or Prakash, right? You know him. He's from Amazon. He's from Swiggy. You ask him to authenticate at the gate, wherever you live. He's authenticated for COVID. His temperature is checked. His face, his phone number is validated. Even when he's home, you look at him from video camera, and you do that every day. Although Ram is Ram, physically you can look at him, but you do that every day. So that is explicit trust model. So multi-factor authentication is pretty much like using Aadhaar, right? Your number first, and then your iris, your fingerprints. It's authenticated every time. Whether you buy a mutual fund, you do your eKYC. Whether you buy a home loan, you do your eKYC. So that's an explicit trust model. And that's the model we want to go for. I'm just giving an example, right, from a laptop perspective, right? So secure boot, that's what we want, that the BIOS or the main imprint, the preamble of your main things you do boots at the same time. Your device, there's a root of trust certificate. It begins. There is a trusted anchor module. There is a CPU microloader which loads exactly, let's say, from block 512 to block 7896. Nothing else can run here. Like it's like a no man's land. There's any program which is modifying here, anything which you do, it will not allow you to do that. Then the OS kernel comes in, which then identified your device. It says your phone has 3 cameras, so much memory, so much access points, Wi-Fi, Bluetooth, mobile data radio, and all that. All that comes later. But initially, this is how it begins, the secure boot. And that's why for 5G, I'm just expanding it. From a phone or a laptop, you want now security to be end-to-end. So the first layer is the threat detection layer. Okay, factory, robotic arm were never meant to be connected to the internet. And now we are saying, hey, wait a minute, you put these IoT sensors and you can now get how many Mahindra chassis were made every hour, and you can show it to your business leaders that, okay, my production from 100 chassis per hour came down to 95. You want that visibility, you want that intent or outcome. But you're putting all these sensors, and let's say somebody comes, let's say some guests have come inside the factory and they're just carrying a phone. Nothing prevents them from latching on. They can be a guest, they are on your factory network, and suddenly they're siphoning data off. That's why you need the threat detection, right? Who's accessing? So who, what, how, where, what time of the day. Just like Aadhaar. Are you both? Okay, the photo match. Is your number matching? Is your iris matching? Is your fingerprint matching? One, 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 one. One plus one plus one plus one. No either or. It has to be an AND function. And then the gated logic says, okay, allow. and even that can be controlled, right? So I'm just given some layers, just food for thought, but just fancy security names. For me, if you ask me, in case you do not know, there are two types of people in the world, we jokingly say, right? Especially when we talk to Reliance or Rakuten, they don't even know. I'll be very honest with you, and I'm just saying this. Um, some people believe our networks are more secure. Some people believe hacks are, I don't think they will hack a data center. It's very difficult. We are in this software export zone. We have the highest security, video cameras, and all that. So, bottom line, there are two categories of people, things, or organizations. First category is people, companies, or organizations which have been hacked. The second category are those who do not know, not scaring all of you. All I'm trying to say is it will happen eventually. For all you know, you could be. For example, again, because we are using Indian examples, let me say so. SBI's, right? All of you know, last August, around same time, I think between August and September, 3.5 million Visa and Master SBI credit cards were siphoned. The data was compromised. Now, let's not go into details of what level of data, but that the data, I mean, 16-digit numbers, your name, the validity expiry, and even the reverse, the CVV digits were compromised. I think that is enough to cause a lot of havoc. Okay. Um, Here's the sad part. When I say sad, it is not a reflection of SBI or something. Technology itself was not evolved that it couldn't detect this even after 13 and a half days. Almost it took them 2 weeks, 14 days to detect the first level of hack. And then, so detect, remediate, react, do everything. So detect, remediate, apply. So this model, right, is failing. So it needs to be the moment you connect anything in IoT, before, during, so before you connect, during the time you connect an IoT device, and even after, it has to be continuous. So all this 6 layers of security have to be continuous. Otherwise, there's huge points. For someone who asked about smartwatches, you may not know, but there were, for example, on the Leh Ladakh border, there are a lot of army surgeons who wear these smartwatches. Since people like to turn them on when they're running, that was used, that data was compromised, okay, to know the trackings. Their patterns was known, which gave an indication on how on the LAC are you running. So you can do havoc if you do not. So the point I'm trying to say is security is not a layer above. Security is actually the first L-1 layer. From day zero, it's like you're designing a house, think about the fence, right? When you decide the height of the fence, think who has access to the fence, what time, who, when, where, how, and then what else you need, right? Then start building the house, okay? So that is the approach. So security first is what we'll need. I'm not saying everyone is doing it, but they will need it, right? It's very imperative. I'll quickly pause here again if there's any questions. And Naresh, can you remind me, is it till 120 or is it till 145? Okay. Any questions, Naresh?
No, no questions. So move forward.
Okay. And a quick time check. How are we doing? Is it till 145 or 125?
1:30, I guess you can close it whenever you're comfortable.
Okay, perfect. Because I just have 2 or 3 industry examples for IoT, but we'll end with this layered stack, right? So,
Perfect.
so by now, yeah, thank you, right? And let me know if it kind of shoots beyond 130. I'm keeping a timer here, but in case I slip, just feel free to pitch in, Naresh, okay?
Definitely, I'll
So,
do that. Yeah.
yeah. So it's a simple stack, right? I know we spoke about the 7 layers, right? The standard TCP/IP or the internet layers. Again, I'll repeat: physical, data, uh, so network, transport, session, presentation, application. 7 layers. IoT is very simple. There's things, So your watches, your robotic arm, your traffic lights, your phone. That's the biggest, the most visible IoT object you carry everywhere, pretty much for half a day around with you. And there is applications. I'm just simplifying it. There are things which you want to see, detect, control, monitor, modify, but you don't want to touch them, code them. You want to do it through an application. That part is clear, right? An application for now, imagine your app banking, imagine a simple application like MyGate, imagine a Swiggy, imagine a Amazon, imagine whichever application, even a Beam or whatever you are used, even one application which you are used or an education learning software. In middle is the magic of IoT, the blue and the orange layer, right? That's what we have covered today. Software defined networking, which itself has the network part, the TCP/IP, the routing part, the compute part, right? You're computing the control data plane elements. The storage part, you're making a decision. Where do you want to storage? How effectively do you want? Do you want to compress? Do you want to decompress? Is this redundant pattern of data? Can you use, lossless compression? All those decisions get done in the orange infrastructure layer. What the nicest way I can think is think about your watch making millions and millions of packets, and the orange layer now has segmented maybe 500,000 buckets. It then feeds to the blue layer with clear 10 buckets of data, which is normalized. Okay, data from Subodh's smartwatch, data from Naresh's electricity meter, data from Prakash's, just giving example, right? Smart meter, data from Saravanan's FASTag. So as you go further up the stack, it's normalized. And why? The word normalize here means it's modeled. So remember that example? All people with blue shirts enter the room, then you model. All people with blue shirts, collared, right? So golf shirts or t-shirts sit on this side, that side. All people with science degrees sit on this side. All people with this much marks within that sit on this side. So you're just modeling, keeping. And so that light blue layer makes it finally ready for the application layer. And that is the layer at which, for example, an iOS or an Apple SDK or an Android SDK takes nice lineated data and just makes good use of it. Okay. And now I put the technical terms which I think should be individual courses or topics of research, very, very focused research and development. Right? Everything, yes, is APIs and all. It's very loose to say hardware, software, middleware, firmware, but this is what we're talking about, right? So edge compute in IoT is called as fog. Why fog? Cloud is up there, a little cloud closer to the ground, we call it fog. Yeah, you can barely, it's like closer. The fog is slightly below the cloud. So we call it as fog computing. Okay, so I'll just now break this down. Think about a sensor, think about an oil factory. We have put millions of sensors. It goes to the edge node, right? So now you see all that millions and different types of data. It is transforming data from a canonical format. Okay, so we got all the different colors, flavors of data. Then I'm categorizing. When was it generated? Where was it generated? Is it time series data coming through, maybe oil rigs making insertions in the ground, the rigs, revolving, the calibration of the rigs. Is there any local action I need to perform? Hence that mech node or the fog node, right? The fourth layer is, okay, now that I know this has to go to a specific target, will it go back to the office or the oil office, ERP office, which tells me from an app the wear and tear of the machine? I've just used 5 layers. You can bring as much layers as you like in IoT. The thumb rule is the more layers you bring closer to one, the better results you get, right? Because that is a place where data is generated. You compare this to a smart city or a smart hospital or a smart education campus example. Where are the students? The students are in the campus, they're generating the data. If you put a local network there, an edge node, you're basically doing all the compute, filtering, evaluation, shaping, marking, policing closer to the data source and acting on it. So basically, to summarize, right, you have to get value from data. That part is clear, right? Nobody wants an app-based banking if you're not getting value. If somebody has made the world's most colorful app for banking and I cannot do a fund transfer, I would never, and you would never even use that app, because the most important thing you do, probably after you're checking your bank balance, is do a fund transfer. So you got to derive some value. Okay. The problem is things are everywhere. As someone rightly said, we have probably 10 connected things now. We may have 100 maybe in 2 or 3 years. Maybe all our flower pots may have. Maybe all our dag and cot um, furniture may have some sensors. Right now, just from computing devices, which means devices like tablets, phablets, mobile phones, which have a CPU and an IO mem, you might go to things which have nothing, but just a little sensor. That's it. If you have a costly, for example, thing which you want to make sure nobody steals, you just put a sensor on that for real-time tracking. So you got to make sure the app is somewhere in between and giving you that value. Okay, and this is how the world will now look like again further up. So it goes without saying, right, that this is the place where as cars, robotic arms, medical devices get connected, you have to make sure the apps are also moving along with the devices in software. That's why this yellow arms, right? And we call this as an IoT distributed data platform. Let's break this down into some industrial use cases, very dominantly called as smart city cases, right? So you need automation monitoring. You have 4,000 bus stops. You can put CCTV cameras right near the nearest light pole. Anyone who's standing at the bus stop gets free Wi-Fi, gets illumination. 100 meters to the left and right of bus stop, you can put parking lot and meters. You can do so many things. Okay. Fleet management. That is what the likes of Amazon, Flipkart, Snapdeal. They have huge inventory. They want to track all their devices. These are just e-commerce players, but think about factory producers. Okay, and below each use case, I've just given the network speed, okay, latency, and the battery type. And that I'm just going to spend just maybe a few minutes talking about that battery type. It's very clear by now that IoT doesn't live in the house. IoT is outside, right? Your gate or even your security person at the gate has an IoT device. He's not connecting it to 220 volts AC. Your sensor is not connected to a 220 volt AC cable. It's completely on battery. That's why IoT is also called as LP WANs, the IoT network part, low power WANs. So the first design criteria of IoT after the network and the routing part is how much battery juice can you squeeze? If you put sensors at IP, at CCTV cameras, if you put sensors on your cars, if you put sensors on your wearables, if you put sensors on your gas or electricity meters, you don't want a person to come every month, every year just to replace. How irritating is that? Not just irritating, it's a downtime. So you want sensors which just are turned on demand. When I'm transmitting data, I need to do some IO. I need power. I will take power from the battery. That's why those battery lives are given. So typically, gas electricity meters have a battery life of 10 to 12 years. They use a protocol called LoRa, long range. That's a IoT LP WAN. So IoT has its own WAN, right? From the thing to the cloud is a WAN, wide area network protocol, and that's called as LP WAN. And there are two types of LP WANs: LoRa WAN, and there is a narrowband IoT. So narrowband IoT is what the Airtel, the Geos, and the Vodafones will give you. It's a licensed one, and LoRaWAN is something like your Wi-Fi, free. Okay, by free I mean you don't pay for the spectrum, but you pay for how many devices you're connecting, and that also Tata and Reliance have built. So Unlimit is India's biggest LoRaWAN between Reliance, Huawei, Tata, Cisco. So if you suddenly say, I have a house, I have a building which has 5,000 IoT points, you get licenses starting from 5,000, 10,000. And as every 5,000 device you add, you pay 100 rupees, 200 rupees more. But all the data is collected on the WAN. This is a LPWA, remember, low power WAN or wireless access, waste management, right? So waste management, what is the biggest thing in waste management? Are trucks going in the right lanes? Only on those streets where the trash or the kachre ka dibba, as we call it, right? Is that 50% full, 60% full, segregated? So you see that wireless thing, if you put wireless sensors, we suddenly become sensing points, trash bins, which can smell, detect volume, look at the density, and even the constituents if you want it. And they can then signal over a cloud network or a LoRa network that I need a truck roll today. So if your lane has 400 trash bins and only 20 of them need to be picked up, the municipality can make a intelligent decision and say no. Unless the threshold is 40%, we'll not send a truck. Because we know by looking at all of your 400 trash bins, none of them is above 80%. 80% is a cut-in threshold, right? So they'll keep simple software rules. Even if one trash bin is 80% full, send a truck. So what are the immediate advantages? You're saving on fuel, right? I know this sounds easy to say, but once the networks are implemented, you can put anything on it. Practically anything. If has a stray cat or dog overturned the trash bin, give that feedback back to the owner. So this has been implemented in Monzo in Italy, right? So Italy has this, Barcelona has this similar example. There is even a theft of telephone cable wires. So we did this. So very beautiful use cases. You can exactly track everything. You name it, you can track cable drums. People can steal those huge cables, and this cannot be stored. These are normally stored for 2 or 3 weeks, and then the fiber or the telecom people start rolling it out. So geofencing, right, is someone, if you put a sensor on that cable drum, you can exactly know if somebody is carrying it out. So if you move up the IoT stack, again, I'm just putting the 5G IoT stack together. Um, you have many protocols. You have many open APIs and protocols to choose from. Uh, at the word which I think the blue layer is where it gets interesting. Just like your browsing data, HTTP, there is a constrained access protocol now. Okay, low power, only transmitting on demand. Unlike Ethernet or wireless router, right? Even if you're not browsing and your wireless router is on, you're just sending something, right? It is sending beacons. It is validating SSID. It is saying it is on. There is something going on. You cannot have this model in IoT. No data, nothing. Save battery, complete shutdown, not even standby or sleep, complete shutdown. The moment there is data, activate, right? In nano milliseconds, start transmitting. So MQTT, right? Message queuing telemetry transport. That is like a very low power version of TCP/IP. That's the popular transport protocol. And then there is device data and applications. Okay, so yellow, physical, IP, non-IP data. Uh, in case any of you is wondering, Subodh, why is the green saying non-IP data? More than 80% of all the factory data is non-IP, non-TCP/IP. So all the factories were there before us, right? We were born where we got things produced by factories, right? From Maggie noodles to Boeing airplanes. They were not running on TCP/IP. Our mobiles and laptops run on TCP/IP. Uh, the factories run on Profinet, Modbus, Profinet, SCADA. These are all, nuclear reactors, all these people. So you have to get that non-IP converted to IP to do something meaningful. Remember, IoT is Internet of Things. It is not, non-Internet of Things, right? So even that conversion has to happen. So just bear in mind, this is how the protocol looks like. Okay, so that is completely RESTful based API. You measure the device, you detect. There needs to be a common vocabulary to define IoT data and concepts. Again, I'm moving to Python, I'm moving to JSON for object notification. And you need to do the standard things. If you have installed an IoT smart meter, you need to have OTA. So the standards body for IoT is called as 1M2M. Okay, I'll just keep this for Q&A for us. That even 5G and IoT both need to be secure. So I'll leave this as the final message for all of us. So you have IoT and machine to machine. Please remember the threat is they have weak inbuilt security. So just like I said, it's difficult to steal a home. Very difficult, right? You can't carry a home. It's slightly difficult to steal a router, small, big, medium. It's very easy to steal an IoT thing, phone, your Fitbit, smartwatch, or fitness band, whatever thing you make. So that's very weak because those physical things are there. Plus, people can just code it again. Also, 5G and IoT have a lot of virtualization thing. When I say SDN, network function virtualization, so there are a lot of attacks which can come even at the API protocol level. And there's always going to be new and legacy technologies coming in together. Like someone of you asked, will 4G and 5G work together? What happens when blockchain comes? So each country has its data privacy laws, right? So GDPR by Europe, data loss protection or prevention mechanisms have to be in place. for any of you who are interested in this, and I think we should encourage this to all our students, DSCI is defining the standards, right? So Data Security Council of India is the parent body. We all contribute to it from Cisco, and individually, I'm also someone who's writing the standards for 5G and security there. So we all work closely there just to make sure this threat mitigation also happens. So I'm quickly going to thank each one of you. I know I was standing between you and a long day, a morning, and lunch especially. So thank you all for the listening. Thank you all for the great questions you asked, which kept me honest and humble. And it was a sheer delight to interact with all of you and be associated with GTF. And lastly, Nirmal, Naresh, Saravanan, thank you all at ICT Academy for just making sure this happens smoothly. Over to you, Nirmal. Thank you.